Okay, so this is a short, quick intro to multivariable calculus. We'll talk about all the a little bit, a tiny bit about each of the chapters we're going to be going through this semester, and then we'll start actually going through the material. This video should probably be 13.1 and 13.2. This week we're doing 13.1, 2, 3, 4, and 5. 13.3 will be a separate video, and 13.4 and 5 might be a video. The two sections done together, possibly. I haven't recorded those yet. Okay, let's do our intro first. So this is multivariable calculus. And what is it? It's exactly what the title says. We're going to be doing calculus with multiple variables. So in a way, the main focus of the class is to study functions which, instead of just taking one input, x, it can have multiple inputs, and then it has some output. All right. We're going to be studying the calculus of these kinds of functions, derivatives, integration, all the same stuff that we did in first and second semester calculus, except in a multivariable setting. Things are going to be a lot more complicated because of the multivariable setting, but this stuff is a lot more useful than single variable calculus because of the multivariable setting, because multivariables allows us to model much more interesting things. For example, much more interesting things in real life, where oftentimes things are in a multivariable setting. Things depend on more than just one variable. Okay, let's see. Let's go through very quickly each chapter bit by bit or one by one, just to see what they're kind of about. Chapter 13 is the basics. It's mostly just setup. There's not going to be any calculus in chapter 13. We need a lot of setup because there's a lot of tools that are necessary to study multivariable functions. Again, because of the added complexity of having many variables. By basics, essentially I mean vectors. So we're going to talk about vectors. We're going to talk about dot products. We're going to talk about cross products. We're going to talk about visualizing vectors. All the stuff that we need to get going with the multivariable calculus. And again, a lot of chapter 13 we're going to be covering this week. Most of chapter 13, in fact. Okay, chapter 14 is vector valued functions. So this is one kind of extension of the kind of functions that you looked at in single variable calculus. So it's actually slightly different from the function that I just wrote down up here, which is what we are going to spend most of our time working with in multivariable calculus. These vector value functions are going to be functions which take in input, let me call it t, because oftentimes we'll be thinking of the input as time. And the output is not going to be a number, right? As in, regular single variable calculus. The output is going to be a vector. Okay. So we're going to talk about the calculus of these kinds of functions, differentiation, integration, and so on. So these are going to be useful, for example, if you're modeling motion, someone or something moving around in the real world. All right. Okay. So this will take chapter 14 will take about a week or so. Yeah, roughly a week or so. Slightly more. Okay, chapter 15 is where we actually start to get going. So this is going to be f of x, y, z. So multivariable functions. Up until the midterm, we're going to be doing this chapter pretty much. We're going to be doing mostly derivatives. Um, they're going to be telling us the same things derivatives told us in single variable function calculus. But again, we're in a much more complex setting. And so derivatives are actually going to be a much more complex concept. It won't be just f prime anymore. There'll be derivatives with respect to each of our variables. So that makes things a little more complicated. And then we'll have this new concept of a gradient, which is super useful and super important. I'm going to be spending quite a bit of time on that. But overall, we're going to be doing all the same topics that you did in single variable calculus. There'll be the chain rule, which is going to be significantly more complicated than the one variable version, but you need it in order to actually take derivatives. We're going to be doing optimization, so max-min problems. And we're going to be doing something new, Lagrange multipliers, which basically is allows us to do max-min problems in a special setting. So these two topics actually go together and are the most important things that you see in calculus. So hopefully in single variable calculus, your instructor told you that this section in single variable calculus, the max-min section or optimization section, usually it's called, was the most important thing that you learned in single variable calculus. And it's very much still true in multivariable calculus. In a way, optimization problems, max-min problems, Lagrange multiplier, max-min problems are what run the world. All of physics, in a way, are run by max-min problems. All of physics, roughly, essentially, works by minimizing energy or minimizing some quantity. You see this also in other fields, of course. Economics, you're wanting to optimize, find the maximum, find the minimum of various quantities. So super, super useful. This is the most important topic that we learn in this class. Okay, so this is going to be roughly right before the exam. So hopefully you'll have some time to kind of absorb the material before the midterm. Okay, next, 16 is, so 15 was derivatives, roughly, just as a kind of shorthand. It was derivatives. 16 is integration. Integration of multivariable functions. And again, because we have many variables, integration is actually far more complicated than integration with one variable. One of the key differences is that you'll need to be able to draw pictures. You'll need to be able to draw pictures of the domain of integration. So this is something that you never saw in one variable calculus, because in one variable, right, if you want to integrate a function, right, it was always over some interval, which was just a line segment or something like that, an interval. No problem, right? You just integrate from A to B. But now with multivariable functions, let's say two variable functions, we're going to be integrating over regions in the plane. And so because regions can be kind of curvy or not straight in particular, the boundaries are going to be very, very complex. And so you're going to have to be able to draw pictures in two variables, for example, this guy right here, or in three variables even, for when we integrate functions of three variables. All of this stuff, in this class, we're restricting ourselves to 2 and 3 variables, but everything we talk about extends to even more variables. So f of x, y, z, w, f of x1, y1, z, f of x1, x2, x3, x4, whatever, however many number of variables you want to work with. And in real life, these are the problems that that often come up because, again, real life depends on many variables. Okay. So chapter 16 is all about integration and all the various features of integration that that need to be discussed, extra features that need to be discussed because of the fact that we have a multivariable setting. Okay, in a way, you can kind of think about all of this as setup for chapter 17, which is the actual vector calculus. So the way this class is structured, I guess the title of the class is actually vector calculus, or calculus, it's calculus 3. If you go to a quarter system university, oftentimes this first part from chapter 13 to 16 all the way up to here is one quarter class, and then vector calculus is going to be a separate quarter class. So we're a semester system, so we kind of combine the two into one class. So vector calculus is very, very, very in a very short description. Basically, it's going to be fundamental theorem of calculus. So very big quotes here. There's a lot of stuff going on in this chapter. It's an entire chapter, and again, it can be an entire class in a quarter system. But roughly, if you boil it all down, it's the fundamental theorem of calculus. So essentially, it's going to be you have an integral of a derivative, and that's going to be integral on the boundary. Just like the regular fundamental theorem of calculus, f prime of x dx is equal to something to do with the boundary, right? F of b minus f of a, right? Here you have an integral of a derivative. We're going to have integral of derivatives. And then on the right-hand side, we're going to have something to do with the boundary where the derivative is not appearing, right? On the left, you have f prime. On the right, you have no f prime. So it's going to be the same idea up here in vector calculus. We're going to have the derivative of a function or some quantity. It's going to be vector fields often. And on the right-hand side, the derivative will disappear. But instead of working inside the region over here or over here in one variable calculus, on the right-hand side, we're going to be working on the boundary. All right. We'll go through this exact same discussion when we get there, because it's a super important kind of boiling down of what the chapter is about. Whereas if you kind of don't have this global point of view, it'll look like there's several sections of strange theorems that seemingly don't have much to do with each other. But in fact, they're all roughly fundamental theorem of calculus. In particular, what I mean is we're going to be doing Green's theorem. We're going to be doing Stokes' theorem. And we're going to be doing divergence theorem. Super important for stuff like electromagnetism and things like that. But again, all of these are very roughly fundamental theorem of calculus. But again, because we're in a multivariable setting, fundamental theorem of calculus is can be thought of as a lot more complicated than in single variable calculus. Okay, all throughout this semester, whenever possible, I'll give you hints as to why you might need to take the next few classes of calculus. So typically, I guess the calculus sequence would be single variable calculus, maybe 2 quarters or 2 semesters. Then you got some sort of multivariable calculus like this class, some sort of vector calculus like this class. And then next up would be linear algebra. Some universities actually do linear algebra first, but I think it's more typical to do the multivariable first, so linear algebra, and then after that, typically differential equations. So this would be after our class. So I'll try to as much as possible, give hints as to, during this class, give hints as to why you would need to care about linear algebra and why you would need to care about differential equations. And hint for differential equations is that it's related to optimization. And again, I already said optimization runs the entire world. And so anything that's related to optimization is going to be important. Okay, let's see. So, in terms of the structuring of the class, like I said, the midterm will come after we do the max min. It's a good stopping point because it's such an important topic. So I wanted to make sure we did it before the first midterm so that we could have 2 exams possibly covering the topic. In any of my calculus classes, optimization appears on every exam that it's eligible for because it's, again, the most important topic in the class. The final will be cumulative, and the way I've structured the class, so we've got 8 weeks in this class. We're gonna do in week 7, so vector calculus roughly has 4 sections. We're gonna be doing 3 of them in week 7, and then 1 of them in week 8, and then the final exam is gonna be Friday of week 8. So week 8 technically will only have 1 section, and I've done that so that hopefully you'll have some time to absorb some of the actually pretty complicated functions or complicated theorems that you see in vector calculus. Of course, the price we pay is that we have to go a little bit faster in weeks 1 through 7, but it's not disastrous. We're not going to be going at a ridiculous pace. Well, we are because it's summer, but it's not going to be completely undoable. All right, so again, week 8, hopefully, if everything goes to plan, there'll only be 1 section, probably on a divergence theorem. That'll be new, and so you will have time to absorb the material before the final exam. Okay, I think that's it for the introduction. Let me actually start with the class. So 13.1. So we're gonna, in this particular lecture, we're gonna be doing 13.1 and 13.2. 13.3 is, I think if we tried to fit 13.3 as well, the lecture would be a little long. So